Is this thing on? Okay, I thought I'd dress a little nicer today. Try to, I don't know, ease you guys into the science a little bit instead of jumping right in. Trying something a little different. I have to roll my sleeves up, otherwise I'm deeply uncomfortable. All right, I thought I'd dress a little nicer to get you guys in the mood for some fancy, elegant, at least I think it's elegant science that we're going to be talking about today. Some stuff that I've done that I'm pretty proud of and excited to show you. Instead of jumping right in, I thought we'd just start with a little blurb. In case you're new here, hi, I'm Will, and I make videos every 2 weeks. 2 weeks ago, I posted a video that did not do very well, but I think it's a pretty good video. At the very least, some very interesting concepts. I basically simulated the process of biological evolution in order to optimize a neural network, and I think that was a pretty cool project. So if you're interested in that, go check that video out. Now that video was about my forced myography project. Today we're moving on from that, but I just wanted to give a quick update on that project. I was able to achieve a more successful result than the one that was shown at the end of the last video, where I actually was able to detect through my wristband whether or not I'm doing the classic I love you Spiderman gesture or not. So that was pretty cool, but still there needs to be some work done on the generality of that device. Very thankful to PCBWay, the sponsor of this video, because their hardware was integral to making that project very easy compared to what it had been before I had their help. And we're going to talk more about PCBWay closer to the end of this video, because they're going to help me realize some of the scientific work that we'll be talking about in this video. So with that intro done, I think we'll just go ahead and jump right into the content of this video. There's a lot to cover, so I hope you guys are awake and primed, or maybe you're just doing the dishes or something. I don't know.
For those of you who haven't had the pleasure, this is Charlotte, my 8-legged robot project inspired by the elegance and efficiency of a real spider. Up until now, I've demonstrated Charlotte's development in several videos, showing how her legs are flexure mechanisms driven by a nutation transmission, such that simple rotation at the input can create a complex gait trajectory for the foot. And I've used her as a prop for comedic purposes. Since I graduated with my PhD in June, and no longer have to contend with the hours eaten up by grad school, I thought it was about time for us to take Charlotte back to her roots. What is this robot actually for?
So as a PhD student, I went to a few conferences where I was lucky enough to experience cutting edge work in robotics. At one conference, there was a keynote that I was extremely grateful for. This was given by a researcher adjacent to the field of robotics, but it was a non-technical presentation. Rather, it was a retelling of this individual's experience escaping a horrible situation. Sorry in advance for being vague during this discussion. I don't really want to draw public attention to this person. And more importantly, this person's experience is unfortunately not unique. So it wouldn't really matter which geopolitical event I'm describing. So I want you to try to imagine, maybe you don't have to imagine, I certainly do, being a member of a marginalized group. Your regional culture defines you as an ethnic minority or religious minority or both. It already must be uncomfortable, I can only assume. But then there's this extremist group who wants you to be significantly more segregated, subjugated, or worse. And now imagine this group suddenly, almost without warning, obtains control of your country by force. This person was a PhD candidate. I was a PhD candidate. This person was teaching a class of undergrads, and I've done the same. In the middle of their programming class on this random day, it happened. It seemed bad enough when I watched this on the news, but what this person described was harrowing. It was scary, but they finished their class, tried to pretend everything was fine so as not to spook their students. It's really hard to picture my university empty, the security saying, "Go home, the country is lost." After this takeover, escaping the country was near impossible. This person hid, waited until the situation had calmed, and then was able to escape with the help of an organization which helps academics at risk find positions in safe countries. And from what I understood, despite the situation having cooled somewhat before they left, the escape was still non-trivial. I want you to imagine being on the road, not knowing where the next checkpoint will be, and you have to avoid these checkpoints at all costs. After the presentation, another audience member asked the question I'm sure many of us were thinking, what can we do? How can we help? And I was humbled to have the opportunity to have a brief conversation with this person after their presentation where I followed up. Do you think that there really could be engineering solutions that could have mitigated some of your hardship? And to my surprise, they were like, yeah. They specifically mentioned the difficulty with anticipating these checkpoints and stated if there were a robot that could scout ahead and check if certain routes are safe, That would have made things much easier. So this gave me a lot to think about. The idea of giving civilians a cheap personal reconnaissance robot. This could be useful for people who suffer from political persecution, but also for anyone walking the streets hoping for a safe way home. This may sound kind of out there to a lot of you at home, but look, tech like this is going to exist whether we like it or not, and I'd rather everyone have access to it than just the people with the biggest wallets. And whether we like it or not, the necessity of protection from government can reach anyone at any time. Either I'm subconsciously trying to cure the world's arachnophobia, or Charlotte could be the solution to this problem. I started the Charlotte project just to see if she was.
Let's say we want Charlotte to fill this role, and ask the question, what do we require from her? And how can we elevate her from cool hobby project to life-saving technology? Now in this video, we're going to be focusing on Charlotte's propulsion system, that is her motors and legs. It will be a while before Charlotte reaches her maximum potential, possibly years. Until that point, my goal is to let you purchase useful prototypes on my website, dragline.tech. The current project milestone, which I aim to reach in September, is to release Charlotte as a configurable locomotion platform for robots, just as a body, motors, transmissions, and legs. If you want to build a little robot, no matter what it does, you should let Charlotte make it walk. In this video, you'll see why. To get Charlotte ready for this milestone, I'm going to need some major upgrades. Right now, she's slow, heavy, weak, and the battery runs out pretty fast. These upgrades will happen in a few steps. When you design a robot, every decision flows from your requirements. For Charlotte, I began by studying the biology of tarantulas, their body weight and speed, and translating those into engineering terms. My goals were lofty, keeping the body length below 100 millimeters, keeping the total weight below 90 grams, which is about the same as a tarantula, having the battery last at least 4 hours during walking on flat ground, achieving a maximum speed of greater than 0.3 meters per second. It's about half a tarantula's pace, allowing Charlotte to support a payload of at least the body weight, 90 grams, and serviceability. I want the legs to be swappable in under 10 seconds. Now, there's no guarantee a combination of specifications like this is even possible from a physics standpoint, but we're gonna get as close as we can. It's important that Charlotte remains compact and agile. So let's see how delusional I am with this chart by bringing some cold, hard science to the table. To the table. Because it's a table. All things that walk have a gait cycle, the repeated motion of the legs that create propulsion. So even though Charlotte has 8 legs, this allows me to focus on only one for the time being. At the input of one leg sits a simple wheel, which rotates continuously to create the gait cycle. I'm assuming 2 phases during the gait cycle, the lifting phase and the non-lifting phase. These phases are broken up angularly by the fraction c, which I'll just assume to be 1/2 from here on out. Lifting requires more torque on the input than non-lifting. This is where our body weight and payload specifications come into play. Some amount of torque, which we'll call tau L, is needed to just swing the leg during the non-lifting phase. This is a result of the leg design. Extra torque kicks in during the lifting phase to support body weight plus payload. We can assume the extra torque is being exerted as a result of the load on each of half of Charlotte's legs over the lever arm L, which is also a result of the leg design. We'll call the combined torque for the lifting phase tau W. As a result of the torque differences, these phases will also exhibit different speeds, omega 0 for the non-lifting phase and omega W for the lifting phase. This is where our ground speed specification comes in. We can be pretty sure the lifting leg will move a bit slower, so it would be wrong to assume what would have been a linear relationship between the unloaded leg speed and the ground speed. Every gait cycle, the leg creates a stride, which is the forward distance where the foot makes contact with the ground, and consequently the distance the robot moves forward. The amount of time in which this can occur determines the speed.
It's simple physics. Calculate the velocity v in relation to the trajectory t, in which g, gravity, of course, remains a constant.
Each phase contributes part of this time, but how much? These equations for duration are simple ratios of angle moved by the input to angular speed. The question is, how much slower is the lifting phase? Since we know the extra torque, we can consult the torque speed curve, a property of all actuators. In DC motors, this is a straight line running from stall torque at 0 speed to no load speed at 0 torque. This can be modeled with this equation. We can even consider the addition of an external transmission, like a gear ratio, with advantage G between the motor and the leg, where the torque of the motor is lower than the leg input and the speed of the motor is higher than the leg input. And we can consider a situation where one motor is driving multiple legs. So let's say we know one point on this line, and we want to know another point. We know the vertical component of this other point already. We don't need to know the intercept of this line, just the slope. We know the rise, the increase in torque. Then we solve for omega W. And now we can plug this in to derive the gate cycle period. Let's assume the stride also comes from the leg design and is some multiple of the lever arm from before. Velocity, again, is estimated from the stride and the period. After rearranging some terms, we derive a clean function linking desired ground speed to the non-lifting leg input speed, with some new constants. If we plot this function, we can see how it is shifted from the naive linear relationship which does not consider the lifting phase of the gate cycle. Instead, we see a linear asymptote. Reversing this function is trivial. In all of this analysis, we have built-in relationships for the characteristics of the DC motor. Resistance, torque constant, and stall torque are already included. From these, we can also calculate the supply voltage. I built a calculator on Desmos, which is one of my favorite free tools, so I could play around with these parameters, and it seemed like I wasn't going to get anywhere by playing around with sliders manually. It would be much better to have an optimizer do that for me. But there are two parameters we can't just pick values for. Leg torque and the effective lever arm all come from the geometry of the leg, so we got to model that too. Charlotte's legs consist of a 4-bar-ish linkage with flexure joints. I say 4-bar-ish because it's the plane of a 4-bar linkage hinging back and forth, and the angle of the linkage input and the angle of the hinge are coupled by a nutating or tilting mechanism. That's how we can get a simple rotation to create a complex gate trajectory in 3D space. Shocker, I built another Desmos calculator with a live animation of this leg from 3 views. 7 parameters define the leg. The models in this calculator are largely trigonometric, but it allowed me to get closed-form analytical functions for the foot trajectory in 3D space. See here how that trajectory changes in real time as I adjust the parameters. L, the lever arm, becomes half the extent of the trajectory in the z direction, which generally seems to be zf at theta equals 0. I also want to call attention to the fact that the stride, which remember we are assuming is twice the lever arm, also limits how close these legs can be placed to one another. If 2 legs are closer together than their stride, their feet will bump into each other. We need to allow some tolerance for the real-world thickness of the legs, giving us a formula for leg separation. Because we have 4 legs on one side of Charlotte, the minimum body length we can expect is 3 times this leg separation. Given that we specified a maximum body length of 100 millimeters earlier, we need these legs to be at maximum 33 millimeters apart. These models also allowed me to get closed-form analytical functions for the angular trajectory of all the flexure joints. This is important because the combined flexing of all of these joints, which each have a little bit of stiffness or resistance, create the resistance or torque that is felt at the input. There are other sources of torque, mainly friction, but we won't consider that for now. It might come back to bite us. I built an analytical stiffness approximation from published research, mainly this 2023 paper, Insights into Bending Stiffness Modeling of Elementary Flexure Hinges, by Simir Moschini and Matteo Palpicelli from Polytechnic University of Marseille. I really hope I didn't butcher any of that. I'm so sorry. The total amount of energy stored in the joints must be the same as the total amount of energy that has been transferred to the leg via the input, assuming no losses. All we have to do to get the torque input is to take the derivative with respect to the angular position. Maybe you'll remember that from physics class. Now here's where something really interesting happens. You see how in some places the torque becomes negative? From the differential relationship this has with the energy stored in the leg, this corresponds to places where the energy in the leg decreases. This means that the energy that you put into the leg, eventually, you get it back. So the average torque on the input is, in theory, 0 without losses. Now I still need an estimate for input torque. this assumed constant torque that's needed to make the legs run in the absence of any load. This is a key input to my other model. For this, I'll take a conservative estimate. That is the maximum of this theoretical torque trajectory.
Once again, my playing with this calculator made it really clear I couldn't get anywhere while just messing around with these 7 parameters. We need to run an automatic optimization, but now I have just the model for the job.
Every optimization requires a cost function. I chose a cost function that balanced several objectives, matching target foot trajectories, hitting a desired stride length, keeping the foot on the ground for as close to half the trajectory as possible, and keeping leg torque low. I can adjust the weights of the cost function to balance the objective's relative importance. SciPy's free optimization tools make it easy to combine your cost function with your model and automatically search for designs that meet all constraints. I eventually came up with 2 leg configurations, one that prioritized more objectives having to do with trajectory shape, and another that prioritized minimizing leg torque and maximizing stride. With these 2 configurations in hand, I can now use their respective leg torque and lever arm as parameters in the next optimization to select motor resistance, torque constant, and transmission ratio to minimize required battery capacity, no load motor speed, supply voltage, and stall torque. The result of this optimization was disappointing. I've been an engineer long enough to know that any motor and battery combination with these characteristics was going to be way too big for Charlotte to carry. Be sure to check back in 20 years to see if motor and battery technology has improved at all. I even tried to see if reducing the number of legs per motor from 4 to 2 would help at all, but of course it doesn't make much of a difference. Sure, each motor is doing half the work, but you have twice as many motors. You can't beat physics. So I elected to take a different approach. Instead of forcing my apparently delusional requirements onto the model and letting it optimize the motor and battery characteristics, I'll select the motor and battery characteristics based on what I already have in stock. The motor I chose is one for which I previously took measurements and analyzed for this video. So check that out if you want to learn more about how to measure a motor for its characteristics. And with these characteristics fixed, I instead focused on letting the optimization take the model of Charlotte as close to my requirements as possible. This yielded something more promising, or at least more possible. I decided to stick with 4 legs per motor, so Charlotte would only have 2 motors. Even if 2 legs per motor improve some aspects of Charlotte's performance slightly, I'm basically doubling the weight of the robot, leaving little room for a payload, if any. I also decided on leg configuration 2 because it has the larger stride, which slightly improves the theoretical ground speed.
So this entire study serves 2 purposes. 1, I can now revise my requirements and specifications table so my goals for Charlotte are a little more achievable. And 2, I now have built-in knowledge of all of the parameters needed to redesign Charlotte.
Okay, not dressed so nice now. So this video is already pretty long, so I'll try to keep it brief. I was able to print one leg whose design is based off of the results from all the optimizations, so it's pretty flexible. But there are actually more flexible materials out there. And that brings us to the sponsor of today's video, PCBWay. Now, I've partnered with PCBWay a lot because they have a lot of amazing manufacturing and fabrication services to offer. They've made pressure vessels for me, they've made PCBs for me, but they also have 3D printing services, and that encompasses pretty much all 3D printing technologies that exist. Stereolithography uses ultraviolet light to cure a resin into a solid, and you can do this with resins that are actually really flexible once they're cured. Luckily, PCBWay offers this technology and a really flexible material, and it seems like it has some pretty good reviews. So all I have to do to get a super flexible leg from PCBWay is export this leg design as an STL file, then simply drag it into PCBWay's interface, answer a couple questions, and we're good. This leg is going to be here pretty soon, so next video will get a chance to test it out and test it against the materials that I have in stock. So click the link in the description below for $5 off their amazing manufacturing services. Whether you want CNC machining, PCB fabrication, or like I'm trying now, 3D printing. So thank you to PCBWay for sponsoring this video and many of my projects, and especially Charlotte. You can see they've already built Charlotte's main control board here. So definitely the Charlotte project would be progressing a lot more slowly if it wasn't for them. And speaking of Charlotte's current model, I actually want to point out that through this optimization, we've already started to make Charlotte quite a bit smaller. That's really exciting because my goal for Charlotte is to shrink down her size so that she is pretty stealthy. Now, even though Charlotte is going to be smaller than the current model, according to my optimization, she'll be able to achieve a ground speed of 0.1 meters per second. That's actually about 3 times the current model speed based on what I've measured. And we can be pretty certain of that because of all of the modeling we've done. I'm sure I haven't done everything perfect, but the modeling and the optimization that I've done gives me some confidence in sending this design right off to PCBWay, for instance. I've modeled it, you know, I can be pretty confident that it's going to work. And in doing so, I've saved myself time, I've saved myself money, I've gained quite a bit of confidence, aura increased 10,000%, and hopefully soon we're gonna have a little baby Charlotte running around. So I hope you enjoyed this breakdown of how I mathematically derived Charlotte's new design, and I hope you'll tune in next time where we'll start and hopefully finish to build Charlotte's new body. That being said, I'll let you guys go. Enjoy the rest of your Friday or whatever day of the week it is. Stay amazing, stay safe, and I'll see you guys